In our first section of chapter 2, we're going to learn about relations and functions, which is essentially a good way of showing relationships between two variables. We have four different ways to represent what we call those relations, given at the top here. So that's going to be ordered pairs like your XY pairs that we're used to using eventually in graphs. A mapping diagram, which we might have seen before with an input and an output. Table of values, which again represents those same input and output, just in a different format. And then, of course, graphing it, which we can always use with those same two coordinate systems. For our first example, again, if I'm just asked to represent that information in four different ways, I had my answer written out ahead of time just because we do have a little bit of a writing here in terms of putting that into four different types. But if I want to represent four different months in four different temperatures, again, those are going to be essentially my two variables. I can just choose my input variable, in this case, to be the month, and my output variable to be the temperature. We just want to think if there is a cause and effect relationship, it's probably the month that advances that causes the temperature to go higher. So if I'm trying to represent that in a few different ways, again, you can pause it and try and get all those ways copied or try them out yourself if you had a chance beforehand. We do want to be able to represent that a little bit easier and represent those the actual values. So rather than saying January, February, March, and April every time, if I'm trying to describe that as my variable, I can just assign that to a value. So first month, second month, third month, and fourth month of the year. First way is, again, by using what we call those ordered pairs. And notice that what I did is I put that in a set for my bracket notation. Guess I actually forgot the parentheses at the end of that set there. But as long as I'm able to group together each month with its corresponding temperature, month we just used to represent that as the month of the year. So that was 1 for January, and so on and so forth. Just grouping those together just like your XY coordinate pair. Again, we could also represent that using what we call as a mapping diagram, so an input and an output, using the same kind of input on the left-hand side for your x's, or in this case months, and the resulting temperatures on the right-hand side. Again, that's going to be your output or your usual y value. You can also put that same information in a table instead of a mapping diagram. So again, months on the left, temperature on the right. Or as we're used to, we can put that into a graph, and again, with each point representing my month for the x-axis and my temperature for the y-axis, as we did on the others. And notice also, if I was skipping some information, you may see this occasionally on graphs, I'm skipping from 0 straight up to 65, so to represent that missing information, we're just going to leave that kind of a little bracketed off symbol on the left-hand side there, so we just jump straight to 65 for our temperature. So if I want to describe relations, it's going to be important to describe what we call the domain and the range of a relation. Whenever you think domain, you just want to think x's, and whenever you think range, you want to think y's. As long as you remember which one's which, that's always going to stay consistent. So all I have to do on a question like this, where if I want to identify domain and range, for the domain, again, that's just going to stand for all my x values. So if I just keep track of those, okay, what I'm going to do is I'm going to put that in kind of a bracket to create a set. I know that -3, 0, 2, 9, and 23 are all the x values. So that's literally all I have to do is represent that as my domain, and just those values are going to go into the domain. We're not going to use the y values. Again, that's going to be for our range. So if I'm trying to describe the range, again, just the y values, 14, 7, 0, -18, -99. We could also just put those in order from least to greatest in order to maybe make some comparisons a little bit easier if I had like more questions going on with this range. So I'm kind of going in reverse order as it appears, but in least to greatest form. If I arrange that from, again, just the y values and list each one once, that's going to be what I use for my range. So trying that with the next set, again, this is just as easy as just recognizing x's and y's. As long as I put from this set all the x's in your domain and all the y values in the range, it looks like all my x's go from -7 to 0, all the y's go from 20 to 60, going up by tens. And as long as I remember which one's which, that's really all we need for domain range. Again, domain being x's, range being y's. So a function is going to have a specific type of relationship, and that's going to be where a domain corresponds with exactly one element of the range. So to demonstrate what we mean by that, we have an example in the first case where it is a function, because again, even if I'm using these kind of like arrow notation on my mapping diagram, each time I use a value from the domain, we only use that once for a range value. So like -3 is not repeated, 0 just goes to one value, 4 just goes to one value. An example where this doesn't work, so the next relation is not going to be what we call a function, because notice if I have these two ordered pairs, 4, -1, and 4, +1, that means if I'm using that same x coordinate of 4 and I'm mapping that with two different y values, that's not going to be what I call a function, because again, I can't repeat that value from the x. So trying that again real quick by yourself. If we have a domain listed on the left and range listed on the right, trying to decide yes or no, is this going to be a function? Again, you guys are free to try this before we look at this in a second. But know that first one should not represent a function because, again, this value in the domain 2 is mapped to two different y values, -3 and +3. So I think, yeah, going to +3, not -1 there. I wrote that down originally. Corresponds to -3 and 3. But again, I can't repeat that value from my x with two different y's because that's going to break my relationship for a function. If I'm looking at that next example, just by pointing this out, we do see a few repeats, like we see 14 being used twice, we see 7 used twice, see -7 used twice, but this is actually a function, so we are not breaking our rule here. Each time I use an x value, we use like -7, 9, 14, and 7. Notice there's no repeats. No repeated x values is a good sign this is going to be a function. Notice we do have a repeat y value, but that doesn't matter. I can repeat a value in the range, I just can't repeat that value for my domain. So if I had like 14 as two separate x values, that would not be a function. 14 being used twice as a y value is fine for a function. Again, it doesn't matter that I do something like use a 7 for a y and a 7 for an x either. As long as 7 wasn't used for an x coordinate twice, that's still going to be a function. A good way to demonstrate this is something called the vertical line test, which might be something you've seen before. A vertical line test is essentially just a way of finding on a graph the same rule that we knew earlier, is that I can't reuse the same x value with two different y values, and if I do, that's again not going to be a function. So if I want to use that vertical line test to tell if these are functions or not, literally all we have to do, you might have also heard this is the pencil test. You can imagine like rolling a pencil across your paper, and if it touches the graph at any point more than once, that's not going to be a function. So again, we could have points on this first graph where it's not touching any point at all, and that's still fine. Again, that wouldn't violate our vertical line test. And even let's say if I'm on like the very edge of my circle, what I call tangent, if I'm hitting one point that hasn't broken our rule yet, didn't exactly draw my lines vertical, but you can imagine they're going straight up and down. But anytime I do something like this and draw, again, I just need at least one vertical line to pass through twice, and that's not going to work. But as long as I'm using a vertical line and it passes through my function twice, that's not going to be a function because, again, I just passed through twice, and that's going to break my rule for what I need for a function. Again, that means that at any of these lines that I'm repeating, that's the same x value being used with two different y values. So notice the next one also looks kind of strange. Again, we just have like a scattered series of points here. But this actually does work as a function because for any vertical line I draw through those, and again, we can imagine that even in the spaces in between, again, it could still hit a point once, and that's going to be fine for each vertical line. Only thing I'm looking for that vertical line test is I don't want a vertical line to hit more than once for my function. So let's say if I had like this vertical line, if it passes through the point at the top, but if it also passed through, let's say, this point at the bottom, if I move that over a little bit, that would not be a function. But the way this is drawn, yes, it's going to be a function because, again, any vertical line I can draw through that is not going to hit more than one point on my graph. So trying that next one, seeing if that is a function or not based on our vertical line test. Looks like this is a function. Again, I kind of drew my vertical lines through it already, but if I draw those in again real quick, doesn't matter where I draw the vertical line throughout my graph. Every time I draw a vertical line is not going to hit more than once. Again, even if I'm at like the tip of this curve here, it's only going to hit the top and it's not going to hit twice. So since each line I draw through that is not going to hit more than once, that will represent our function. So function rule is essentially just writing what we already had as an equation. So something like y equals 3x plus 2. Only thing that's really changing is now instead of y, I'm just saying f of x. Again, that's how I read this, not f times x, which is pretty common when people see that as multiplication. But we're reading this as a function of x because, again, I'm just replacing the output with a different way to describe that same output. And you can read through the description up above, again, independent variables and dependent variables. But if I'm to use, again, this kind of function notation, really what that allows me to do is to treat this almost like a substitution question. If x is what I'm supposed to substitute, then if I have a few values that I'm trying to find the output for, again, x is always considered the input. I just want to be able to substitute that into the function to find the output. So this is a lot like any other substitution question. If I want to find the input for, again, the output rather, so this is representing the output when I use -1 for x. Again, just like when I substitute, I just want to make sure I can substitute and simplify. If I get 2 plus 5, I think that first output is going to give me a 7. If I try that again, we're just given a series of points here to test. So if I test 3 as an input, again, all I'm really doing is substituting that into the function, -6 plus 5. Simplifying that, I think is going to come out to -1. As long as I'm doing that, it's every point from my input, so -2 times, in this case, 0 plus 5. Hasn't really changed anything. We know it's still going to be 5. If I try that last one, again, this is all we're doing is really just substituting. -2 times 1/2 plus 5 again. If I get -1 plus 5, this last one I think is going to give me 4. So whenever you get a question like this, just think it's like a basic substitution question. They're telling you what to substitute. We just want to make sure we can substitute that in for x. Again, all we're really doing with that f of x is describing this as a function. So we're looking for the output when we're using these certain inputs. So with the answer on that next one, just to reveal that real quick, if I substitute -2, I get 9 back as an output. If I substitute 0, I just get 1. Substitute 5, I just get -19. Again, this is like any other substitution question. Only difference is with that kind of function notation. We're just saying, what's the output of my function when I use -2 as an input? So on and so forth with 0 and 5. So for the next few problems, we can use that same function notation. It's going to be pretty common, especially in a word problem. I went ahead and I described for some of the pieces from that question in terms of what's my input. In this case, the input is the number of bottles from that situation that's described. And we're trying to find the total cost of a purchase. So again, that's going to be what we call the output of my function. If I'm to write this as a function in function notation, we're saying again that whatever the output from the cost is, it's going to depend on how many bottles I have. Again, you want to think of this as that kind of dependent relationship, not the other way around. Again, bottles doesn't depend on like the cost. It's the cost that depends on how many bottles I've bought. So if each one is $1.19, that's going to be $1.19 times every bottle that I buy. That's first of all our function rule. If I'm asked for that part of the question first, that's going to be like our separate answer. And then if I want to do the next part, which is to evaluate that function for 15 bottles, again, this is like any other substitution question that we have. We're looking for the output of the cost when the input is 15 bottles, and that means if I do 119 times 15, forget this actually off the top of my head, so I'm going to leave that blank for now and come back to it in a sec maybe. But yeah, I just want to make sure I multiply that out, and that's going to be my total cost. Actually, yeah, I left the cost off there, so sorry I don't have my calculator handy. For the last one, again, we just want to do those same two things. We're looking for two parts of that question. Just like from before, we want to represent that with a function rule and then also evaluate that if we're buying 4 tickets. There is a way that we consider this, I think, if you're trying to think like each ticket in this situation has a separate shipping fee. That is something to consider here. I just considered that as one straightforward shipping fee. So this is what I chose to model that function with. Again, if x is the input, depends on how many tickets I buy. Again, that's the important part. Cost is going to be my output because first I have to know how many tickets I'm buying. Then if I know that, I can figure out the cost. My function itself, again, what we call that function rule, is kind of like what we do with any other equation. We just decide what's our variable cost and what's our fixed cost. Since we said that it's $40 each for our tickets, that's going to be 40 times x, just like any other equation. And then if 350 or 3.5 is our shipping fee, that's just going to be a standard flat rate that I'm paying to complete my order. So this is, again, depending on the input for x, if I know how many tickets I buy, that's going to allow us to figure out our cost. So you always want to think about what's that input and what's the output in this situation. In this case, if I want to find, again, we're also trying to evaluate this for 4 tickets. If I want to find the cost of 4 tickets, again, that's kind of how we say that in function notation. Cost of 4 is an input. All I want to do, just like with any other substitution question, substitute 4 into the equation where I see an x, and then simplify from there. So in this case, if I'm working through my order of operations, multiply first, and then I can add those two together. Again, 350, I just interpret it as that one fixed cost for the entire order. So if I'm paying 350 for shipping, 163.50 is going to be that total if I'm buying those 4 tickets. And again, you want to multiply that together. Sorry, I just don't have a calculator handy to multiply that last part out. But that is, again, just finding whatever your output price is. That is always going to be based on how many you're buying. So in this case, it's like 4 tickets. In the last case, it was like 15 bottles. You just want to know what's the input and what's the output, and that's going to help set up your function.